Okay, sharing. Happy Thursday. Getting through the week. You're doing it. Week 3. I did want to just quickly point out that this has been up there for a while. I don't have a pointer on here, so I'll point by hand. You've got the graphs of the toolkit functions. That's from last week, but I think I forgot to mention that I put it in the textbook and other resources section of our Moodle page. Okay, and then I found this, which I knew I had a feeling I had made, but it's really just a summary of how to store and recall numbers on your calculator, or the one I think most of you have at least. Okay? So just in case you want that. We've got an ambitious, very ambitious, I'll say, day today. A lot of it is easy on me, hard on you, because I'm just introducing concepts, and then it's up to you to absorb them. So, nothing to it but to do it, if my Notability opens. We'll talk about domain, but in terms of review, I really think that we can just kind of jump in. We talked about domain and range last day. What's the domain? The domain is all the possible values of x that I can put into a function. And then the range kind of depends on the domain in terms of what the outputs can possibly be. Right. We also talked about interval notation and set builder notation, right, which we'll use in our examples. And so that's why I'm just jumping in. Okay. To finish 1.2, so this is 1.2 continued. Those first couple of sections just drag on. You'll find that they pick up and they're a little bit shorter after this. I need my pointer. There. So a piecewise function is a function where the formula that we use depends on the domain. And of course, maybe as a tiny bit of review, remember the domain is the possible values of x. So usually what we use is f of x, which we've seen before, function notation, and then we have equals, and we use one left-hand curly bracket for a piecewise function. And we'll have some formula 1 if the domain is for formula 1, right? And so here we'll restrict the values of x where formula 1 applies. And then we move on to formula 2 with the next domain. What's one example that we have already seen that would be a piecewise function? Well, we talked about height and age. And we said, well, kind of reasonably, it might start to look like this. Right? And so we would have kind of a function for a set of ages. I think we landed on roughly 17 or so, right? And so for x between 0 and 17, we would have this line, this kind of upward sloping line, right? We're growing. And then 17 onwards, right, we would just have basically a horizontal line. Okay. And so that would be a piecewise function. Another piecewise function, we don't really have to deal with this anymore, the cell phone plans. And if you are, you can probably find a better plan. but it was very, very common before, where a cell phone plan might look like this, where there's a base $30 fee. So no matter what you did with your phone, you had to pay $30 a month. That includes 300 free text messages. Can you imagine? 300. Now we just send them willy-nilly, but no. And then each additional text message costs 10 cents. So up to and including 300 text messages, it's $30. And then you get charged an additional fee. Now what we want to do is we want to write a piecewise function to describe this behavior. First thing you want to do is think about what's your input and what's your output in this scenario. The input is going to be x and output is going to be f of x generically. But it looks like the cost depends on the number of text messages that I sent. Right? I can link it back to the number of texts. And so x can be the number of texts, and the output is the cost, right? The total cost. So knowing that, what can we do? F of x, even if you had to solve this, I'm confident that you could solve this problem if I said, oh, I sent 470 text messages, right? How much will I have to pay? You can solve this, right? That's kind of problem solving, but you probably don't set up the formula in a piecewise function, even though that is technically what you're using, right? So what is the formula? So if x is the number of texts, then I know that if x is 300 or less, right, the cost is going to be $30. Okay? So let's start there. So for my first line here, if x is less than or equal to 300, we can put a lower cap on that as well. You can't send negative text messages. And so it's between 0 and 300. Right? That one's kind of optional, but we like to be proper. So now we have this first domain, right? And so if x is between 0 and 300, then the cost is 30. Okay? So then f of x is just 30. And what this is going to look like in terms of a graph is that for up to 300, right, we have this horizontal line. The cost is just constantly 30. And then after 300, what happens? Then we start paying per text, right? So how are we going to capture that in the next domain? Well, if x is just greater than 300, right, not including 300, because we don't want to have any overlap here, then the function will be confused, right? Only one possible output, but that's okay. If x is greater than, let's do it like this, I'll match it, greater than 300, and if you wanted to, you could throw an infinity on there if you're feeling snazzy. It's implied, but why not for symmetry? Okay. then we know we have to pay the $30, but I also have to figure out how to pay that additional 10 cents per text message. So if X is the number of text messages, then what if we did something like this? Start with 30. Here, let's start at 30. And then I build up by 10 cents per message. But you want to be careful. It's not just times X, because that could be confusing, right? Because if X is 200, then you're not past that, but then you're still multiplying, and it kind of makes a mess, right? And so what we want to do is we want to set X minus 300, right? Because those first 300 are free. And I'll give myself just a tiny bit more room here. This is the sneaky part, so I'll do it in pink. Because then, what does this X minus 300 become if I've sent 302 text messages? I get 302 minus 300, so then I'm paying for just the additional 2 text messages, right? And so this is kind of sneaky, right? But once you've seen it, right, then hopefully you'll remember that trick, right? It's not a trick, but it's good to have up our sleeves, right? If you need to adjust for ones that have been paid for already. So then the domain says that this first one applies, right? And so, yeah. Nice. Good. So piecewise functions, first thing you want to do if you have an X, like 200, right? Then you see, okay, well, which domain would 200 be in? It'll only be in one of those, right? It would be in this first one, so then f of X is 30. Let's do it with a function. So now we're not building the function, we're given the function, which is what I prefer to do on a test, right? I don't want to make you build a function and then use it, because that's kind of circular. But I do expect if I give you a function, you'll be able to use it. We're going to evaluate f of 2, f of 4, and then I snuck in a negative here because it was so boring. Negative 3, f of negative 3. So if we find f of 2, the input is 2, so x is 2. And we need to figure out where 2 is going to go here. Is 2 less than 0? No, it's not. 2 is greater than or equal to 0. So then f of x is x squared, which means 2 squared. So f of 2 is 4. Can you imagine if they'd all been positive? Do you see how boring that is? They all use the x squared function. Boring. How about f of 4? F of 4, so 4 is positive again, which means that the function is x squared. So I get 4 squared, which is 16, right? Thank you. Now, f of negative 3, if x is negative, right, then my function is x minus 4. So -3 minus 4 is -7. So you take your input, see where it falls in the domain to find which function applies, and then you evaluate that function. Uh-oh. What if we have to write an equation for this piecewise function? Okay. I'll zoom in so we can kind of see it better. This is where the toolkit functions really come in handy, right? This looks like a parabola, right? And if we're lucky, and we will be, it's just x squared, right? Nothing's happened to it, okay? And so how do we check, right? I suspect that this might be x squared. Well, I can check some inputs and check the outputs. And if it matches what I'm expecting it to be, then I can move ahead and assume that it's x squared. And so if I put in 1 squared, I get 1. Feeling good. How about -2 squared? I get 4. I'm ready to commit to this thing, just x squared, right? So recognizing those toolkit functions, especially something like x squared, and then just being able to confirm that it is in fact x squared is going to be really helpful. Okay? Otherwise, that looks overwhelming, right? How am I supposed to know what this is? Well, it's just x squared. Okay? When is it x squared? It's x squared, and I'll draw it down here on the including -2. So notice this closed dot, open dot. We've seen that before in our intervals, right? So up to and include, or starting at -2, including -2, and then going to 1, but not including 1, right? Getting really, really close to 1. But then another function takes over. What's this function? This function doesn't care what x is, it'll just always be 2, right? And so here, this is going to look like f of x is equal to 2. Here I'll specify f of x is x squared. And f of x is going to be 2, picking up at 1, including 1, right? And then going to infinity. Right? So now we have to write the equation for this thing. I have 2 pieces in my piecewise function, so I need to make room for, in my curly bracket, for 2 lines. Right? And so, like this. We've already talked about the first one. Now, usually what we do is we list the domains from left to right, right, as they appear, just because it's a little bit easier to find your appropriate domain if they're increasing, right, as you move down your list. In theory, I guess you could have them all jumbled, but that would be kind of messy to use, right? So, first of all, we did the hard work and we said, well, f of x is going to be x squared if x is between -2 including -2 up to 1. And then we said x is just going to be 2 if x is greater than or equal to 1. And you can stop there if you want to, but I really like the symmetry of having x between 2 values, because then I don't really have to think about which way the signs are going so much, those inequalities. And so I'll tack on an infinity on there. little end cap. But saying x is greater than or equal to 1 is sufficient, right? That implies it goes to infinity. Nice. So those are some piecewise functions. Any questions? In that case, we're ready for our next section. Section 1.3 is on rates of change and the behavior of graphs. So the rate of change, I think of it as just the slope. Right? You might remember the slope of a line. Right? But the rate of change describes how the output quantity changes in relation to the input quantity. Right? The output being your y's and the input being your x's. And we can trace this back to rise over run, right, which is your slope. Right? But the units on a rate of change are the output units per the input units. So rates of change can look like a population of rats increases by 40 rats per week. I really, really don't like rats, but I'm fascinated by them. I don't know. It's like, I know. Well, there's a lot of kind of interesting studies. Like they did a study in New York where there's obviously lots of rats. And they found, I think it was like a 7-block radius. The genetic makeup of these rats in these neighborhoods, kind of just 7 neighborhoods or blocks apart, were completely different, which leads us to know that they don't really move, right? They just kind of hang out in their area. They're not really breeding even 7 blocks away, which is not what you would think. Anyways, I really don't like rats, but I find them fascinating. They tried to do rat birth control, but it doesn't work because you can't make sure that they take it. It's really difficult. Anyways, too much rat stuff. Now you guys are going to think, well, I think she actually does like rats. No, I don't. Ugh. How about this one? A barista, there we go, earns $9 per hour. So the dollars per hour would be the rate of change. Okay? And a farmer plants 60,000 onions per acre. Right? And so that would be the rate of change. We will work with the average rate of change. Okay? The average rate of change between 2 input values is the total change of the function values, which is the output values, which is your y or f of x, divided by the change in the input values. What's this a fancy way of saying? Rise over run, right? And so really, this is going to be rise over run. We have lots of different ways that we could calculate the average rate of change or talk about the average rate of change, but I find that rise over run is the one that's most familiar. But it's really the change of output over the change of input. And have you guys seen delta yet? Delta means change. So I'll just make a note of that just in case. This is a delta, which means change. Y2 minus y1, x2 minus x1. Really what that means is I have 2 points, right? I have a point, let's use a different color here. I have a point x1, y1, and I have a generic other point x2, y2. We think about a straight line here. Can draw a straight line. The average rate of change, if we had to find the rise over run, well, this little guy here maps down to x1 and y1. And the second point maps down to x2 and y2. Trying to find some colors, maybe some green. This distance is the rise. The rise is going to be y2 minus y1, right? The change in the y's. And the run same thing, is going to be x2 minus x1. So then if the average rate of change which is so long to write, is equal to the rise over run, what that's really equal to, y2 minus y1 over x2 minus x1. As long as you pick which one will be your 0.1 and which one will be your 0.2, it doesn't actually matter which one you assign to which. Of all these formulas that we have, right, this one is the one that we'll be using, right? All the other ones are kind of conceptual. Yeah. What we'll find though is sometimes we can have functions that look like this, and we can still find the average rate of change. But for a straight line, it is the slope. But that's the reason I'm avoiding the term. So nice. We can have, so this author, he loves doing things, so a function as a table, a function as a graph, and then a function as a function, a mathematical function. And so we'll see examples using all of them. If we have a function as a table, f of x, we're asked to estimate the average rate of change on each interval. Here we have the input in the table and the output in the table. And so it is implied on each interval of x. We always talk about the interval of x, never y. But we're just getting started, so. On the interval of 4 to 8, square brackets because it's inclusive of 4 and 8. Otherwise, we wouldn't know what to do. But then the average rate of change is so long. I'll put the equal sign down below. Well, let's start with y2 minus y1 over x2 minus x1. Remembering, that y is just f of x, right? So if you prefer to read your f of x as just a y, right, it might be helpful, especially in this scenario where I've only given you the y2 minus y1 formula. So I know x is going between 4 and 8. So what I want is I have x equals 4 and x equals 8. I have the corresponding outputs, right? So if I let this be 0.1 and this be 0.2, just the order that they appear, I'm going to get, and I'm tempted to write across the page, which is not something I like to do, but such a little example. 16 minus 6 over 8 minus 4. Is 10 over 4 anything nice? Sort of. 2.5. So the average rate of change between 4 and 8 is 2.5. How about on 4 to 10? Whoops, need square brackets here. Average rate of change, again, is y2 minus y1 over x2 minus x1. I'm just going to cram it in there. Oh, you know what? I'll use a different color just so we can see. Oh, change the color of some of this stuff too. That's confusing. There. Oh, whatever. Because then I can use this green. So from 4, the output is 6, but now I'm moving out to 10, and all of a sudden I'm at 26. So now I'm going from 26 minus 6, that's my rise, and I have 10 minus 4, that's my run. I have 20 over 6 is nothing nice. I'll do 3.3. But you probably sensed that the rate of change would be higher, right? Because all of a sudden I'm moving from 8 to 10, which is not a huge distance, right? I've moved from 4 to 6, 6 to 8, 8 to 10, but all of a sudden I'm jumping from 6 to 10 to 16 to 26. Huge, right? So it's kind of taking off. Using a graph, we can calculate the average rate of change. We're just going to estimate the outputs, of course. They should be relatively obvious, but and I decided to make duplicate graphs for A, B, and C, just so that they don't have to be so crowded. A is on 0 to 1, which means I have my inputs, right, 0 and 1, but I need to find my outputs and maybe a brighter color here. I know that when x is 0, looks like y is 0. Right? And I also know that when x is 1, I see that y is 1. Right? So the points that I have are 0, 0, and 1, 1. So the average rate of change, I wish there was some better shorthand for that. Not for us. y2 minus y1 over x2 minus x1. So when you're using a graph like this, right, I do recommend that you jot down your points, and then it'll be easier to look at your x's and your y's. Because now my y2 is 1 minus 0 divided by x2, which is 1 minus x1. So I just get 1. 1 minus 0. What would happen if you flip these, right? I used 0, 0 as 0.1 and 1, 1 as 0.2, reasonably. But what if I flip them? Then I would have 0 minus 1, negative 1, over 0 minus 1, negative 1, negative 1 over negative 1 still makes positive 1, so it doesn't matter. How about on 0 to 2? Oh, sorry, 1 to 2. So now my x is going between 1 to 2. So I have 1, 1, and 2, 4. Can I be lazy and just write the formula instead of the name? The average rate of change equals, I give myself permission. Fine, you can have permission too. Y2 is 4. Y1 is 1. And x2 is 2. X1 is 1. 4 minus 1, I'm going to go with 3 over 2 minus 1, which is 1, giving me at 3. What do you think will happen between 0 and 2? So we found the average rate of change between 0 and 1 is 1. And then between 1 and 2 is 3. Right? What if I look at the entire interval now, 0 to 2? Right? It is the average rate of change. Right? Let's see if it checks out. Now we're looking at 0, 0, between 0 and 2, and 2, 4. Really cramped here, but that's okay. I have 4 minus 0 over 2 minus 0. Give me at 4 over 2, or just 2, which is kind of what we suspected, right? So the average rate of change, of course, depends on the interval that we're interested in. Nice. We can get a little bit fancier, and instead of y2 and y1, right, let's call this y2 and this y1. We could use f of b and f of a, where b must be x2 and a must be x1. This is the same as, right, as before. So if we have a function f of x, the average rate of change on the interval a to b, which is going to look like this. I have something like this. between A and B. Remember, f of x is on my y-axis and x is on my x-axis. Then in terms of function notation, this is at f of A. This is at f of B. So we can scale up our y2 minus y1 over x2 minus x1 into something just a little bit snazzier, right? But we're still doing the same thing, and we can say, well, what if I use f of b minus f of a over b minus a, right? We're still doing the same thing. And maybe instead of this, I'll put it beside y2 minus y1 over x2 minus x1. Right, they're the same. What you'll find is these tend to be a little bit longer. And so together, I've picked that I want to do B and E. And then before I post the notes, I'll insert my work for for A, C, and D so that you have it. But I want you to try it on your own and see if you can kind of pick through it, right? Because it's one of those things. Yeah, I can stand here and do it, but it's better if you do it and then check your work. So we have a function now, right? So notice we moved through a function as a table, function as a graph, and now we have a proper function as a mathematical function, and that function is x squared minus x. We want to find the average rate of change on each interval. And so just to jot this down, I have f of x is x squared minus x, and the interval that I'm interested in is 1 to 3. Now, since I have this interval, this function here, right, then I'm going to use the f of b minus f of a version of the average rate of change. What's our first step? Let's highlight what our a is. It's going to be 1, and our b is going to be 3. Okay. What else do I need? So then I have my b minus a ready to go. I also need my f of b as well as my f of a before I can put them together, right? So I like to solve those just separately first. F of a is f of 1. Wherever I see an x, I'm going to replace it with a 1. And so I get 1 squared minus 1. 0. What's my f of b? Put them side by side so we don't have to scroll so much. F of b is f of 3. So wherever I see an x, I'm going to replace it with a 3. So I get 3 squared minus 3. 9 minus 3, 6. Okay. Now we're ready. Average rate of change using the function notation f of b minus f of a over b minus a. Notice how I like to jot down the generic formula and then plug it in. Because now it's just plug and chug here. 6 minus 0 over b, which is 3, minus a, which is 1. I get 6 over 2. I go for 3. Nice. So even though we have no idea what x squared minus x looks like, we can still just use the formula to find the average rate of change. And because I'm adding the work for C and D later, I'm just going to start a fresh page with E, because otherwise it might be confusing. I'll make a note here. Add A, D, oops, A, C, and D. Hopefully I remember. I will. Because E, I want to find the average rate of change on the interval from A to A plus H. And if you've done any sort of calculus, this is probably ringing a bell. Ugh. Okay, we're not going to go beyond this, but we do need to kind of talk about how we use it. And that's about it. So the interval that I want to deal with is on, the H's aren't looking very good. What does this mean? Graphically, if I have some sort of graph, maybe it looks like this, some sort of function like this. If I'm able to put in a generic A, right, and then move out a distance of H, well, that puts me at A plus H. And of course, here I have f of A, and here I have f of A plus H. So if I'm able to develop a formula for the average rate of change from A to A plus H, then really what I could do is then I could backtrack and use that formula for all the previous examples, right? Because if we're looking at A to A plus H, well, if I want to do -1 to 3, then my A would be -1, and my H would be 4, right? To get to 3. So you'd need to pick out what your A is. That's easy enough. It's going to be the starting point. But then your H is whatever you need to add, right? That distance that you want to move. But then you can use this generic formula, which is why, I know, surprise, surprise, I wanted to do this one together. Okie dokie. Well, we need to remember our function, f of x is x squared minus x. Let me just confirm that because I don't want to do it with the wrong one. It's true. My A in my formula is A, but my B in my formula is going to be replaced with A plus H. So here, A equals A, but B must be A plus H. Slightly more complicated, but not too bad. What's the next thing we did? Well, we found f of A and f of B. F of A in x squared minus x is A squared minus A. F of B is, I'll clarify here. Sorry. f of a equals f of a, whereas this is just for properness. Properness is really f of a plus h. F of a plus h, wherever I see an x, I'm going to replace it with a plus h, making sure I keep a plus h as one package, one item, right? And so it's going to look like this. And how do I do that? Well, I use brackets. A plus h squared minus a plus h. Keep a plus h just together. Okay. Now the average rate of change we know is f of b minus f of a over b minus a. I built all my components, now I need to put them all together. And so I have f of b, and what I like to do is keep f of b in big square brackets and f of a in big square brackets, again, just to denote that they're kind of a package deal, right? So f of b is this a plus h squared minus a plus h minus, need these brackets on here because if I'm subtracting, I need to distribute that negative. Oops. Big square brackets. Maybe I'll just bump this down a line so I can make a quick note that this is f of b, of course, and this is f of a earlier. Divided by b, which is a plus h. Again, keep it as one thing, minus a, which is a. So again, this is your b, and this is your a. As long as you kind of slow down and take it methodically, it's not so bad, right? Plugging in all your values, and then we can expand and simplify. All right. A plus h squared. That one's going to make a mess. Why? A plus h squared is a plus h times a plus h, which means I have to, what do you guys call, do you call it feed the chickens? Is that the one? We have to distribute it, okay? And so we have to do that, but first I'll just write it out. And then minus a minus h. So I'm distributing this subtraction in here just to try to simplify things a little bit. And then I'm going to move on to the minus a squared and then plus a. Right. Our goal is to simplify, so expand and simplify, collect like terms, and get it to be as kind of small as possible, I guess. Divided by a plus h minus a. What's nice is immediately I see some cancellations I can do. All right. So I don't have to lug them around. No, you don't have to do that. You don't have to cancel things until the end, but I have a minus a plus a, that can go away. I don't need to drag those around. And how about an a minus a? And what's kind of cool is if you've done everything correctly, okay, and a nice way to check it is that this h will cancel in the end. Okay? If you're unable to get this h in the denominator to cancel, something went wrong. Okay? So it will go away. Just we have to be patient, a little bit patient. And so here, note this h in the denominator will always cancel. Eventually. I'll add that. Take some time. Okay. Looks like our job is to feed the chickens. I think is really cute. A times a is a squared plus a times h is a h plus h times a. Now, I will just write as a h. Right. A times b is the same as b times a. Just to make it a little bit easier to see what happens. You can. I'm not very good at expanding, and so I always write out the individual terms. Okay? But if you're good at expanding, go for it. All right, you can skip that step. And then finally, plus h squared. And then I don't want to forget about my minus h minus a squared. And this is over h. I can simplify a little bit. I see an a squared minus a squared. That's nice. Just like I foreshadowed. Right. I have a lot of h's in here. So let's simplify a little bit. I have 2a8 plus h squared minus h over h. I like to pull out a common h out front before I cancel. You're welcome to, if your brain can do it, right? Take away one h, take away one h, take away one h. That's fine, but I don't like to do that. But that's just personal preference. I like to pull out the h that I'm about to cancel, and then I'm left with 2a plus h minus 1 divided by h. It's also, I find, a little bit easier if it's been a while since you've kind of pulled out common multiples and things like that, then it's easier to see what happened. Because now h divided by h is 1. 4 divided by 4 is 1. So now my answer is 2a plus h minus 1, which is my average rate of change on any interval from a to a plus h. So now we have the formula for the average rate of change of f of x is equal to x squared minus x on any interval a to a plus h. Should we try it on the one that we did? Make sure we get the same answer. So we have 2a plus h minus 1. What if I go back up here? On the interval of 1 to 3, right? If A is my 1, then H. So confirm that 1 to 3 using the average rate of change now I've forgotten 2A plus H minus 1. Here, A is 1, and H, A plus H, H is 2. Now I have 2 times 1 plus 2 minus 1, 2 plus 2, 4 minus 1 is 3, which is the same as what we found. But if we're doing a lot of these average rates of change, then finding the generic formula for it is going to be a lot quicker, right, than doing them all individually. So that's kind of cool. Kind of cool. Any questions about that? Oh, yeah. This one? Is it this part? How about I change this to A plus H is equal to 3, but A is 1 plus H is equal to 3. So H must be 2. Had a feeling that was it. Nice. Good. Good. So like I said, those take some practice and they can be quite tedious, but I always enjoy tedious because then it means you know what you're doing and you just kind of do it. I'm not going to say it's easy, but it gets easier. There's a lot of terminology with functions, okay? And so increasing and decreasing, I think intuitively, you have a pretty good idea of what it means for a function to be increasing. So for example, if you had to just guess, is this function increasing or decreasing? Looks like it's increasing, okay? And this one looks like it's decreasing, right? And you're absolutely right. But why? So this one is increasing and this one is decreasing. Yeah. Function is increasing if the function values increase as the inputs increase. Really what we can talk about is if f of b is greater than f of a, so if we have some generic a, b, then of course here's f of a and here's f of b. So if f of b is greater than f of a, which is the case in this scenario here, for any two input values a and b, in the interval where b is greater than a. Or if you prefer, and this is why we work with the average rate of change and calculate it, then the average rate of change of an increasing function is positive. Right? So if you calculate the average rate of change and you find that it's positive, then it's increasing. So why would that be? Well, the average rate of change is f of b minus f of a over b minus a. And because I'm going to do this for the next one too, I'm going to cheat and copy paste right away. If it's increasing like this, so we decided this is increasing, right? Then f of b minus f of a is going to be a positive number, right? And so what we can do is we can say this is a positive number. And if this is what an increasing function looks like, then b minus a is also going to be positive. And a positive over a positive is a positive number. And that's where we get this from, right? The average rate of change is going to be positive. Whereas if you have a decreasing function, then what you'll find is that the decreasing function is negative. So again, we're going to force b to be greater than a, so a to b. So from a to b. Now, here's my f of a. Oops. And roughly, there's my f of b. Now looking at f of b minus f of a, well, f of b is smaller than f of a. Right, so I'm going to get a negative number in the numerator. And I need just one more line, but I think I can get it by bumping this down just a smidge. It's going to be perfect. Now I get a negative, but we forced a to be less than b, so b minus a is still positive. A negative over a positive makes a negative. So that's why we can use that rule. And if you have a positive average rate of change, then it's increasing. And if it's negative, then it's decreasing. Luckily, those kind of line up with what you would think intuitively. So given a function, we can determine if it's increasing or decreasing. The lines got all weird, but by calculating the average rate of change, right? And if the average rate of change is positive, then you can say it's increasing. And if it's negative, say it's decreasing. Nice. Which leads us to extrema, local extrema. And I need to check the time because from last day, I feel kind of thrown by my internal clock. It's usually really, really good. Not to brag or anything. But last day it wasn't. Okay. A point where a function changes from increasing to decreasing. What would that kind of look like? Well, it could look like increasing to decreasing. That's what makes a maximum. Here it's increasing, here it's decreasing. And so if we're able to calculate the average rate of change, then we can see if it's increasing or decreasing. And then if there's a change from increasing to decreasing, then we know there's a maximum. Same thing with the minimum, where it goes from decreasing to increasing, makes a minimum. We call them local because there can be more than one maximum or minimum, right? And extrema just means extremes, and minimums and maximums are extremes. From the graph shown, estimate the intervals, and we're going to be kind of generous, but estimate the intervals on which the function is increasing and decreasing and any local extrema. Now you can eyeball this, right? You can see, okay, I have a local maximum here. Clearly it's not the absolute maximum because it keeps going. And one thing about these graphs to remember is that it's implied that they continue off the page, right? But they continue in the same direction. Nothing happens after that. Just go to infinity. Oops, and negative infinity. And so here, this is a maximum. I can see that. And even though it doesn't quite look like this is the minimum, for simplicity, we'll use it at 8. Kind of looks like it's shifted off a little bit, but. So I can just see those, right? Now, let's confirm that, okay, so for it to be a maximum, it has to go from increasing to decreasing. That's true. So here, looks like I am increasing, and then I'm decreasing, and then I'm increasing again. My maximum seems to be at 3 and roughly, let's say 180. Kind of hard to tell ish. Like I said, we'll be generous. A minimum is at 8. And let's see here. Yeah, what's a good guess? Somewhere close to 75-ish. 70? 70? Sold. Just roughly, something reasonable. Right. Now we want to talk about the intervals, where it's increasing or decreasing. And we already kind of, and I am skipping where we could calculate the average rate of change using the graph, right? Just pick any 2 points, maybe between 1 and 2, and confirm that it's positive. But I don't feel like doing that. It's not very fun. It all has to be fun. I'm going to change the decreasing to a different color so that I can, about green. Although that's kind of an increasing color, but anyways. Increasing is blue and decreasing is green. We want to list the intervals where it's increasing. We're going to use interval notation. And just remember, it starts here at negative infinity, right? X goes to negative infinity. And so it's increasing from negative infinity up to x equals 3. Okay. It doesn't include 3 though. Why? Because at the maximum and at the minimum, what happens is the slope is zero. And so it's neither increasing nor decreasing at either of the maximum or the minimums. And so we have to exclude it. So it's increasing up to 3, but not including 3. And then we need to link up the next increasing interval. Do you remember the U, capital U, for union? You can read it as or, right? Here or here. Picking up at 8, and I will make it, I'll write a note about the maximum and the minimum not being included because it's neither increasing nor decreasing, but I want to do this first. From 8 to positive infinity. Where's it decreasing? It's decreasing on the interval from 3 to 8, not including those 2 points. Nice. I'll make the note here. Note at the max slash min. Hopefully that's okay shorthand. So at the maximum or the minimum, the slope, which is really the average rate of change, but the slope is 0. So instead of it, I'll say the function is neither increasing nor decreasing. Which is why we exclude those points from the increasing, decreasing intervals. Yes?
How do you differentiate between that xy coordinate and a set of like the x coordinates?
There isn't really a way except context, right? Yeah, that's a tricky one actually, because they look exactly the same. Right? But context will lead you there. Right? And so the maximum, the slope is 0, so the function is neither increasing nor decreasing, which is why it is excluded from the intervals above. And by that, I mean here and here. Round brackets. Nice. A little more function terminology. If we had something that looks like this, right, where we go from a larger increase to a smaller increase, then notice how it looks like this. We call it concave down. Concave down. Whereas if it's facing up like this, we call it concave up. Usually all I get you to do is just look at a graph, but let's talk about concavity. So when the rate of change is getting smaller, right, here where it tends to kind of level off, then we say the function is concave down. And when the rate of change is getting larger, and like this, and increasing, then we say it's concave up. So a function is concave up if the rate of change is increasing. And the function is concave down if the rate of change is decreasing. So how will you know? You can look at a graph and then it's easy to see, right? If the cup is facing down or facing up, right? But you would have to calculate some average rates of change over a span of x's, right, to see how it's behaving, right? But that's hard, and I'm not going to make you do that. But I do need you to be able to look at a graph and determine if it's concave up or concave down. Because a point where a function changes from concave up to concave down, or vice versa, is called the inflection point. Okay. So from this graph, we want to estimate the intervals on which the function is concave up and concave down. I always find it a little bit tricky, but I feel good about saying this stretch up to -1 looks like it's concave up, right? You have a bowl, it's facing up. And then for concave down, I'm feeling pretty good about that. But what happened here? At some point, it had to switch and be concave up again, right? And so that'll be our inflection point. And for simplicity, let's say it's here. Right. And so we've got these turning points where we go from concave up to concave down and then up. Nothing happens here, right? It's still up, up, up. In fact, it stays concave up after that point. Huh? I did it again. I got to pick a different color. Orange. Down. It's going to be concave up. On what intervals? This keeps going to -infinity, right? So just remember, even though it doesn't show the rest of the graph that's going off the page, it's just going to keep going and going and going. And so it'll be concave up on the intervals from -infinity up to -1, okay? But not including -1 because that's the inflection point. That's where it changes from up to down. So same thing as the maximum and the minimums, right? They're excluded to -1. And it picks up again here at x equals 1 and going to infinity. Or 1 to infinity. Concave down. Going to go between -1 and 1, which I feel like I heard. And you have your inflection points. Inflection at -1, 0, and at 1, -3-ish. I did kind of fudge that one. It's a little bit off, but something reasonable. Nice. A lot of terminology, but you take a step back they all kind of make sense. I hope. Well, I know I still have some time, even though that one's slow. Any questions before we continue with the next section? I know it was an ambitious day today. But like I said, with all those terms, I introduce them, and then they're on you to learn. Section 1.4 is on composition of functions, which I always really enjoy. I think it's really kind of a fun section. So what is it? Well, if you think about a composition, right, it's a combined thing of, well, in this case, functions, right? So really what we're going to do is we're going to take a function and stuff it into another function, right? And you can keep going. You can take those two functions, stuff them into another function, right? And so what are you doing? You're taking the output of the first function and using it as the input in the second function. Okay? So when the output of one echoes in here, one function is used as the input of another, call the entire operation a composition of functions. We usually write f of g of x, which is read as f of g of x. And so here, I'll zoom in here, because remember, if you just focus on g of x, right, when you see those brackets, you're going to read them as of, right? But now I have f of g of x. Right? What does that mean? It means I use x as my input into the function g, and then I use the output of g of x as my input into f of x. And so it's kind of just two or more steps. You can incorporate as many functions as you want, but we tend to tap out at 3. It gets a little wild at 3 even. We can also say f composed with g at x, but I find that that is less leading in terms of what you're doing, right? I prefer f of g of x because it's just a little bit easier to understand. But it does introduce this other operator, which is the composed with. It's just a little open dot. And so what it looks like is like this. F composed with g of x, which you can still read as f of g of x. And so then I tend to read this circle as of, and maybe that helps. But technically, it would be read as f composed with g at x. But like I said, I find that that's less leading in terms of what you want to be doing, right? And so we need to be able to read it. I did write a note here, but if you have f composed with g of x, how I would probably read it as is f of g of x, because then that leads you to f of g of x. And so I'll make a little note here. You could read it as of, even though technically it means composed with, but yeah. What we'll see is in function composition, order matters, right? And so f of g of x is not going to be the same as g of f of x, which makes sense. If you have two different functions, if they're the same, yeah, they'll be the same, right? But usually we have two different functions, right? And g of x has a different output than f of x, and so I'm using different inputs into different functions. So just remember that they're not the same. As an example of a composed function, if we have a function b of t, and it's going to be the number of bushels of apples produced by t trees, then p of b, these all sound the same now, is going to be the profit that can be made on b bushels of apples. So if we want to figure out which one of these two has meaning, only one of them will. First, I'm going to interpret what each of them mean, because that'll help me identify which one makes sense and which one doesn't. B of P of 10, what you want to do is you want to start with the inside function, right? If the inside function is P, right, that's the profit at B bushels, right? So 10 bushels. So now you have the profit at 10 bushels of apples, and you're trying to figure out the number of bushels of apples from the profit of 10 trees. Doesn't make sense, right? And so here, this is going to be the number of bushels from the profit of 10 trees. Try to keep them tight here. Whereas P of B of 10 now my inside function is B, and B tells me the number of bushels of apples produced by 10 trees. So now I have 10 trees, and the output is the number of bushels, and now I have the profit from the number of bushels produced by 10 trees, which I like a lot better and has meaning. And so this is the profit from the number of bushels produced by 10 trees. Nice. That's tricky, right? That takes practice, right? But it is a nice way of introducing function composition, which we use a lot. If we have two functions, we have f of x and we have g of x. Two different functions as tables. So now we can do function composition with tables. And what I want to do is I'm just going to copy these for each of them, because A, B, C, D. Otherwise, it's going to get really messy really quick. So if we have A, asks us to find G of F of 7. G of F of 7, and I should put this down the line so I can write across. Well, my input into F is 7. Let's start there. So I have to be in the F table, and my input is 7, and I get an output of 6. So I can replace F of 7 with 6. And so here, G of 6. Now I take my 6 and walk it over and use it as my input in my g function. And I get 10. It's another one of those where you just want to be kind of slow and methodical because it can get quite kind of cross-eyed working with multiple tables. But just work through it methodically. And I always try to do so write out the function that you're working with, g of f of 7, and then replace the f of 7 with its output, and then replace the g of 6 with its output. Okay. How about B, g of f of 5? Well, same thing. F of 5 is 2. So I can replace f of 5 with 2. G of 2 is 3. Think you're getting the hang of it. F of g of 2. Now our inside function is g, right? Which means I have to start with my g function and my input is 2. And so g of 2 is 3. F of 3 is 7. Can even get crazy and do something like f of 3. Just take it nice and slow. Just write it out. D f of 3. My inside function is f, and my input is 3, so I get f of 7. Right? Now my input is 7 back into f, which means I get 6. Right? So you can even go back into its own function. I think function composition with tables is nice and fun, but let's do it with some graphs as well. And then, of course, actual functions. I did do copy paste, so we're going to do A and then B and then C and then D, but we need kind of clear graphs for all of these. We're given, here's m of x, so here's a graph of m of x, and here's a graph of k of x. So for our first one, we want to find m of k of 1, which means my inside function is k, so I want to be on this graph, and my input is 1. I get an output of 2. So k of 1 is 2. M of k of 1 is m of 2. Now my function is m, and my input is 2. And now I go from here, and it looks like I'm at -1. Kind of similar. We do m of k of 2. The inside function is still k, but now my x is 2, m of k of 2. The output of k of 2 is 0. And m of 0 seems to be 3. Right? So you can use graphs just like we use the tables. How about k of m of 0? K of m of 0. Now my inside function is m, so I start here and I plug in 0 and I get an output of 3, which means I have k of 3 that I want to find. Now, if the input on k is 3, it looks like the output is -2. K of m of -1. K of m of -1. My inside function is m, and I'm plugging in -1, and looks like I'm here, and I get an output of 2. So I want k of 2. In the k function, if I give it a 2, I get a 0 in return. That's it. With graphs, tables, graphs, you know what's next. Proper functions. All right. We're given a function f of p, which is 2p minus p squared. We're going to use it to evaluate f of b, then f of 3x plus 1, which is also a function, and f of the root of p. Now we've already kind of done this, right? When we used f of a plus h, right? We put in a plus h as one thing using brackets, right? And so it's the same thing. F of b, well, that's easy enough. Wherever I see a p, I replace it with a b, and that's it. I get 2b minus b squared. F of 3x plus 1 tells me wherever I see a p, I replace it with 3x plus 1. That looks like it's going to be a little bit more complicated. Maybe I'll do it down here. F of 3x plus 1. So wherever I see a p, I replace it with 3x plus 1, treating it as one thing. So I have 2 times 3x plus 1 minus 3x plus 1 squared. We can call this g of x. If g of x, bless you, is 3x plus 1, right? Really what I'm doing is I'm finding f of g of x. Right? We just haven't called it that before, but we've done it. We can expand this, right? 2 times 3x, 6x plus 2 minus, and I have to, sounds like you guys are stronger expanders than I am. That's okay. That's great. 3x times 3x, I'm going to go with 9x squared plus 3x plus 3x plus 1. 6x plus 2 minus 9x squared. This makes 6x, but minus 6x minus 1. 6x minus 6x, that goes away. And now I have negative 9x squared plus 1. Well, so here, we already know how to do this with functions, right? We just never called it composition of functions. Well, here we're back to simpler times. Wherever I see a p for f of root of p, root p squared, which becomes 2 root p minus p. Nice. Finally, I give you some functions, right? For us to evaluate f of g of p and g of f of p, and we already know they're not going to be the same, right? Because that's what we established. So we've got g of p, which is 1 over p, and f of p, which is the root of p. So you want to be nice and careful here. Let's start with f of g of p. F of g of p, g of p is 1 over p. So really what I want to find is I want to find f of 1 over p. Wherever I see a p in f, I replace it with 1 over p. Looking like this. Oops. My square roots aren't looking very good. The root of 1 over p. Nice. What about the g of f of p? Now my inside function is f of p. F of p I can replace with the root of p. So really what I want to find is g of the root of p. Now in g, wherever I see a p, I replace it with the root of p. And I get 1 over the root of p. This is one of those rare scenarios I'm seeing where they actually are the same, but that's not always the case. How are they the same? If I bring this root, I can rewrite this as the root of 1 over the root of p, but the root of 1 is 1 over the root of p. Becomes the same.
I don't really get it. Why those seven roots?
Do you mean here? There? So because f of p, right, that's our next step. F of p is the root of p. But wherever I see a p, I'm going to replace it now with 1 over p. Right? And so then I get the root of 1 over p as the overall function.
Well, that's it.
Yeah. Yeah, you always want to do them in 2 steps for sure. if we're given f of g of x is 4 times the third root of x squared plus 5, then minus 2, we can find possible functions for f of x and g of x, remembering that g of x is the inside function. Right? You could make it, well, I mean, you could say, I'll move this down. The simplest, but also most useless option would be to let g of x be x. That didn't get me very far. It does work though, right? If g of x is x, then in f of x, then what must f of x be? Then in that case, f of x must be 4 times the third root of x squared plus 5, then minus 2. Because g of x is going into f of x. Another option we could make g of x take up a little bit more space. And I know it's tempting, x squared. That's tempting too. How about x squared plus 5? Right? So then, if we let g of x be x squared plus 5, then f of x would be what? Here. In that case, f of x would have to be, because it takes g of x as its input, 4 times the third root of x minus 2. And so then you'd have 4 times the third root of x minus 2. So this is a trick that we use in calculus quite a bit, right, where we can kind of rewrite a function as a composition of functions. For us, it's just some good practice. Another option could let that whole third root be g of x, right? Usually that's a good choice. And so then if I let g of x be the third root of x squared plus 5, then f of x just has to be the rest of it, 4x minus 2. Now they're kind of even in terms of complexity, in my opinion. But lots of different options. But being able to look at a big function and break it down into a composition of smaller functions is pretty useful. The spacing got all weird. I'm not going to worry about finding the domain of composed functions. Okay, but one thing that you do need to remember is the domain of the composed functions need to account for the domain of the inside function first, right? You can't put in illegal values into your inside function, as well as the domain of the final function. So sometimes we remove values from our domain from the inside functions that we wouldn't see from the final function. And so as an example, in f of g of x, uh, we first find the domain of g of x, and then we carry that through, right? You can't use illegal values into g of x, you'll get no output, right? And then merge that domain. Shouldn't say merge. Find the overlap. That's more appropriate. Then find the overlap with the final function. Often they're the same, and so that's why I don't want to spend too much. Wow, you guys are so polite. Stop, Emily. Maybe I wasn't looking up on purpose. No, I thought I had more time. Sorry. That's the end, but we did it. It was a marathon of content, I guess. But now